right. This is CS50, and this is already week 5, which means this is actually our last week in C together. In fact, in just a few days' time, what has looked like this, and much more cryptic than this perhaps, is going to be distilled into something much simpler next week when we transition to a language called Python. And with Python, we'll still have our conditionals and loops and functions and so forth, but a lot of the low-level plumbing that you might have been wrestling with, struggling with, frustrated by over the past couple of weeks, especially now that we've introduced pointers and it feels like you probably have to do everything yourself, in Python and in a lot of higher level languages, so to speak, more modern, more recent languages, you'll be able to do so much more with just single lines of code. And indeed, we're going to start leveraging libraries all the more, code that other people wrote, frameworks, which is collections of libraries that other people wrote. And on top of all that, will you be able to make even better, grander, more impressive projects that actually solve problems of particular interest to you, particularly by way of your own final project. So last week, though, in week 4, recall that we focused on memory. And we've been treating this memory inside of your computer as kind of like a canvas, right? At the end of the day, it's just zeros and ones, or bytes, really. And it's really up to you what you do with those bytes and how you interconnect them, how you represent information on them. And arrays were like one of the simplest ways we started playing around with that memory, just contiguous chunks of memory, back to back to back. But let's consider for a moment some of the problems that pretty quickly arise with arrays, and then today focus on what more generally are called data structures, using your computer's memory as a much more versatile canvas to create even two-dimensional structures to represent information and ultimately to solve more interesting problems. So here's an array of size 3, maybe the size of 3 integers. And suppose that this is inside of a program, and at this point in the story, you've got 3 numbers in it already, 1, 2, and 3. And suppose, whatever the context, you need to now add a 4th number to this array, like the number 4. Well, instinctively, where should the number 4 go? If this is your computer's memory, and we currently have this array, 1, 2, 3, from left to right, where should the number 4 just perhaps naively go? Yeah, what do you think? Sorry? Oh, OK. So you could replace number 1. I don't really like that, though, because I'd like to keep number 1 around. But that's an option. But I'm losing, of course, information. So what else could I do if I want to add the number 4? Over there. Yeah, so I mean, it feels like if there's some ordering to these, which seems kind of a reasonable inference, that it probably belongs somewhere over here. But recall last week, as we started poking around a computer's memory, there's other stuff potentially going on. And if we sort of fill that in, ideally, we'd want to just plop the number 4 here, if we're maintaining this kind of order. But recall, in the context of your computer's memory, there might be other stuff there. Some of these garbage values that might be usable, but we don't really know or care what they are, as represented by Oscar here. But there might actually be useful data in use. Like if your program has not just a few integers in this array, but also a string that says, like, hello world, it could be that your computer has plopped the HELLOWORLD right after this array. Why? Well, maybe you created the array in one line of code and filled it with 1, 2, 3. Maybe the next line of code used getString, or maybe just hard-coded a string in your code for hello world. And so you kind of painted yourself into a corner, so to speak. Now, I think you might claim, well, let's just overwrite the H. But that's kind of problematic for the same reasons. We don't want to do that. So where else could the 4 go? Or how do we solve this problem if we want to add a number, and there's clearly memory available, because those garbage values are junk that we don't care about anymore, so we could certainly reuse those? Where could the 4 and perhaps this whole array go? OK, so I'm hearing we could move it somewhere, maybe replace some of those garbage values. And honestly, we kind of have a lot of options. We could use any of these garbage values up here. We could use any of these down here, or even further down. The point is, there is plenty of memory available, as indicated by these Oscars, where we could put 4, maybe even 5, 6, or more integers. The catch is that we sort of chose poorly early on, or we just got unlucky, and 1, 2, 3 ended up back to back with some other data that we care about. All right, so that's fine. Let's go ahead and assume that we'll abstract away everything else, and we'll plop the new array in this location here. So I'm going to go ahead and copy the 1 over, the 2 over, the 3 over. And then ultimately, once I'm ready to fill the 4, I can throw away essentially the old array at this point, because I have it now entirely in duplicate. And I can populate it with the number 4. All right, so problem solved. That is a correct potential solution to this problem. But what's the trade-off? And this is something we're going to start thinking about all the more. What's the downside of having solved this problem in this way? Yeah? Yeah, I'm adding a lot of running time. It took me a lot of effort to copy those additional numbers. Now, granted, it's a small array, 3 numbers, who cares? It's going to be over in the blink of an eye. But if we start talking about interesting data sets, sort of web application data sets, mobile app data sets, where you have not just a few, but maybe a few hundred, a few thousand, a few million pieces of data, this is probably kind of a suboptimal solution to just, move all your data from one place to another. Because who's to say that we're not going to paint ourselves into a new corner? And it would feel like you're wasting all of this time moving stuff around and ultimately just costing yourself a huge amount of time. In fact, if we put this now into the context of our big O notation from a few weeks back, what might the running time now of search be for an array? Let's start simple. I'll throw back a couple of weeks ago. If you're using an array, to recap, what was the running time of a search algorithm in big O notation? So maybe in the worst case. If you've got n numbers, 3 in this case, or 4, but n more generally, big O of what for search? Yeah, what do you think? Big O of n. And what's your intuition for that? OK, yeah. So if we go through each element, for instance, from left to right, then search is going to take us big O notation, big O running time. If, though, we're talking about these numbers specifically, and now I'll explicitly stipulate that, yeah, they're sorted, does that bias anything? What would the big O notation be for searching an array in this case, be it of size 3 or 4 or n more generally? Big O of, not n, but rather? Log n, right? Because we could use, per week 0, binary search on an array like this. We'd have to deal with some rounding because there's not a perfect number of elements at the moment. But you could use binary search. Go to the middle, roughly, and then go left or right until you find the element you care about. So search remains in big O of log n when using arrays. But what about insertion now? If we start to think about other operations, like adding a number to this array, or adding a friend to your contacts app, or Google finding another page on the internet. So insertion happens all the time. What's the running time of insert when it comes to inserting into an existing array of size n? How many steps might that take? Big O of n. It would be indeed n. Why? Because in the worst case, where you're sort of out of space, you have to allocate, it would seem, a new array, maybe taking over some of the previous garbage values. But the catch is, even though you're only inserting one new number, like the number 4, you have to copy over all the darn existing numbers into the new one. So if your original array is size n, the copying of that is going to take big O of n plus 1. But we can throw away the plus 1 because of the math we did in the past. So insert now becomes big O of n. And that might not be ideal, because if you're in the habit of inserting things frequently, that could start to add up and add up and add up. And this is why computer programs and websites and mobile apps could be slow if you're not being mindful of these kinds of trade-offs. So what about, just for good measure, omega notation? In maybe the best case, well, just to recap here, we could get lucky. And search could just take one step, because you might just get lucky and boom, the number you're looking for is right there in the middle if using binary search, or even linear search for that matter. And insert 2, if there's enough room and we didn't have to move all of those numbers, 1, 2, and 3, to a new location, you could get lucky. And we could have, as someone suggested, just put the number 4 right there at the end. And if we don't get lucky, it might take n steps. If we do get lucky, it might just take the 1, or constant number of steps. In fact, let me go ahead and do this. How about we do something like this? Let me switch over to some code here. Let me start to make a program called list.c. And in list.c, let's start with the old way. So we kind of follow the breadcrumbs we've laid for ourselves as follows. So in this list.c, I'm going to include standard io.h, int main void as usual. Then inside of my code here, I'm going to go ahead and give myself the first version of memory. So int list3 is now implemented at the moment in an array. So we're rewinding for now to week 2 style code. And then let me just initialize this thing. At the first location will be 1. At the next location will be 2. And at the last location will be 3. So the array is 0 indexed always. I, for just the sake of discussion, though, am putting in the numbers 1, 2, 3, like a normal person might. All right, so now let's just print these out. 4, int I gets 0, I less than 3, I plus plus. Let's go ahead now and print out using printf, %i\n. List bracket I. So very simple program, kind of inspired by what we did in week 2, just to create and then print out the contents of an array. So let's make list. So far, so good. /list. And voila, we see 1, 2, 3. Now let's start to practice some of what we're preaching with this new syntax. So let me go in now and get rid of the array version. And let me zoom out a little bit to give ourselves some more space. And now let's begin to create a list of size 3. So if I'm going to do this now dynamically so that I'm allocating these things again and again, let me go ahead and do this. So let me give myself a list that's of type int star equal the return value of malloc of 3 times the size of an int. So what this is going to do for me is give me enough memory for that very first picture we drew on the board, which was the array containing 1, 2, and 3, but laying the foundation to be able to resize it, which was ultimately the goal. So my syntax is a little different here. I'm going to use malloc and get memory from the so-called heap, as we called it last week, instead of using the stack by just doing the previous version where I said int list 3. That is to say, this line of code from the first version is in some sense identical to this line of code in the second version, but the first line of code puts the memory on the stack automatically for me. The second line of code that I've left here now is creating an array of size 3, but it's putting it on the heap. And that's important because it was only on the heap and via this new function last week, malloc, that you can actually ask for more memory and even give it back. When you just use the first notation, int list 3, you have permanently given yourself an array of size 3. You cannot add to that in code. So let me go ahead and do this. If list equals null, something went wrong, the computer's out of memory, so let's just return 1 and quit out of this program. There's nothing to see here. So just a good error check there. Now let me go ahead and initialize this list. So list bracket 0 will be 1 again. List bracket 1 will be 2. And list bracket 2 will be 3. So that's the same kind of syntax as before. And notice this equivalence. Recall that there's this relationship between chunks of memory and arrays. And arrays are really just doing pointer arithmetic for you, where the square bracket notation is. So if I've asked myself here in line 5 for enough memory for 3 integers, it is perfectly OK to treat it now like an array using square bracket notation, because the computer will do the arithmetic for me and find the first location, the second, and the third. If you really want to be kind of cool and hacker-like, well, you could say list equals 1, list plus 1 equals 2, list plus 2 equals 3. That's the same thing using very explicit pointer arithmetic, which we looked at briefly last week. But this is atrocious to look at for most people. It's just not very user-friendly. It's longer to type. So most people, even when allocating memory dynamically, as I did a second ago, would just use the more familiar notation of an array. All right. So let's go on. Now suppose time passes and I realize, oh, shoot, I really wanted this array to be of size 4 instead of size 3. Now, obviously, I could just rewind and fix the program. But suppose that this is a much larger program. And I've realized at this point that I need to be able to dynamically add more things to this array for whatever reason. Well, let me go ahead and do this. Let me just say, all right, list should actually be the result of asking for 4 chunks of memory from malloc. And then I could do something like this. List bracket 3 equals 4. Now, this is buggy potentially in a couple of ways. But let me ask first, what's really wrong first with this code? The goal at hand is to start with the array of size 3, with the 1, 2, 3. And I want to add a number 4 to it. So at the moment, in line 17, I've asked the computer for a chunk of 4 integers, just like the picture. And then I'm adding the number 4 to it. But I kind of have skipped a few steps and broken this somehow. Yeah? Yeah, I don't necessarily know where this is going to end up in memory. It's probably not going to be immediately adjacent to the previous chunk. And so, yes, even though I'm putting the number 4 there, I haven't copied the 1, the 2, or the 3 over to this chunk of memory. So, well, let me fix. Well, that's actually, indeed, really the essence of the problem. I am orphaning the original chunk of memory. If you think of the picture that I drew earlier, the line of code up here on line 5 that allocates space for the initial 3 integers, this code is fine, this code is fine. But as soon as I do this, I'm clobbering the value of list and saying, no, 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 don't point at this chunk of memory. Point at this chunk of memory, at which point I've forgotten, if you will, where the original chunk of memory is. So the right way to do something like this would be a little more involved. Let me go ahead and give myself a temporary variable, and I'll literally call it temp, TMP, kind of like I did last week. so that I can now ask the computer for a completely different chunk of memory of size 4. I'm going to again say if temp equals null, I'm going to say, oh, bad things happened here, so let me just return 1. And you know what? Just to be tidy, let me free the original list before I quit. Because remember from last week, anytime you use malloc, you eventually have to use free. But this chunk of code here is just a safety check. If there's no more memory, there's nothing to see here, I'm just going to clean up my state and quit. But now, if I have asked for this chunk of memory, now I can do this. For int I get 0, I is less than 3, I plus plus. What if I do something like this? Temp bracket I equals list bracket I. That would seem to have the effect of copying all of the memory from one to the other. And then I think I need to do one last thing. Temp bracket 3 gets the number 4, for instance. Again, I'm kind of just hard coding the numbers for the sake of discussion. After I've done this, what could I now do? I could now set list equals to temp. And now I have updated my linked list properly. So let me go ahead and do this. For int I gets 0, I is less than 4, I plus plus. Let me go ahead and print each of these elements out with %i using list bracket I. And then I'm going to return 0 just to signify that all is successful now. So to recap, we initialize the original array of size 3 and plug in the values 1, 2, 3. Time passes. And then I realize, wait a minute, I need more space. And so I ask the computer for a second chunk of memory, this one of size 4. Just as a safety check, I make sure that temp doesn't equal null, because if it does, I'm out of memory, so I should just quit altogether. But once I'm sure that it's not null, I'm going to copy all the values from the old list into the new list. And then I'm going to add my new number at the end of that list. And then, now that I'm done playing around with this temporary variable, I'm going to remember in my list variable what the address is of this new chunk of memory. And then I'm going to print all of those values out. So at least aesthetically, when I make this new version of my list, except for my missing semicolon, let me try this again. When I make list, OK, what did I do this time? Implicitly declaring a library function malloc, ... What's my mistake anytime you see that kind of error? Yeah, library. So up here, I forgot to do include standard lib.h, which is where malloc lives. Let me go ahead and again do make list. There we go. So I fixed that, /list, and I should see 1, 2, 3, 4. But there's still a bug here. Does anyone see the bug or question? Oh, sorry, say again? I forgot to free the original list. And we could see this, even if not just with our own eyes or intuition, if I do something like valgrind of /list. Remember our tool from this past week. Let me increase the size of my terminal window temporarily. The output is crazy cryptic at first, but notice that I have definitely lost some number of bytes here. And indeed, it's even pointing at the line number in which some of those bytes were lost. So let me go ahead and back to my code. And indeed, I think what I need to do is before I clobber the value of list, pointing it at this new chunk of memory instead of the old, I think I now need to first proactively say free the old list of memory and then change its value. So if I now do make list and do /list, the output is still the same. And if I cross my fingers and run valgrind again after increasing my window size, hopefully here, still a bug. So better. It seems like less memory is lost. What have I now forgotten to do? I forgot to free it at the very end, too, because I still have a chunk of memory that I got from malloc. So let me go to the very bottom of the program now. And after I'm done sort of senselessly just printing this thing out, let me free the new list. And now let me do make list, /list. It still works visually. Now let's do valgrind of /list, enter. And now hopefully all heap blocks were freed. No leaks are possible. So this is perhaps the best kind of output you can see from a tool like valgrind. I used the heap, but I freed all the memory as well. So there were 2 fixes needed there. Are any questions then on this array-based approach, the first of which is statically allocating an array, so to speak, by just hard coding the number 3. This second version now is dynamically allocating the array using not the stack but the heap. But it, too, suffers from the slowness we described earlier of having to copy all those values from one to the other. OK, hand was over here.
Why did you not have to free the temp?
Good question. Why did I not have to free the temp? I essentially did eventually, because temp was pointing at the chunk of 4 integers. But on line 33 here, I assigned list to be identical to what temp was pointing at. And so when I finally freed list, that was the same thing as freeing temp. In fact, if I wanted to, I could say free temp here, and it would be the same. But conceptually, it's sort of wrong, because at this point in the story, I should be freeing the actual list, not that temporary variable. But they were the same at that point in the story. Yeah? Good question. And long story short, everything we're doing thus far is still in the world of arrays. The only distinction we're making is that in version 1, when I said int list bracket 3 close bracket, that was an array of fixed size, so-called statically allocated on the stack as per last week. This version now is still dealing with arrays, but I'm kind of flexing my muscles and using dynamic memory allocation so that I can still use an array per the first pictures we started talking about, but I can at least grow the array if I want. So we haven't even now solved this even better, in a sense, with linked list. That's going to come next. Yeah? How am I able to free list? I freed the original address of list. I then changed what list is storing. I'm moving its arrow to a new chunk of memory. And that is perfectly reasonable for me to now manipulate, because now list is pointing at the same value of temp. And temp is what was given the return value of malloc the second time. So that chunk of memory is valid. So these are just squares on the board, right? There's just pointers inside of them. So what I'm technically saying is I'm not freeing list per se. I am freeing the chunk of memory that begins at the address currently in list. Therefore, if a few lines later I change what the address is in list, totally reasonable to then touch that memory and eventually free it later, because you're not freeing the variable per se. You're freeing the address in the variable. Good distinction. All right, so let me back up here and just now make one final edit. So let's finish this with one final improvement here, because it turns out there's a somewhat better way to actually resize an array as we've been doing here. And there's another function in standard lib that's called realloc, for reallocate. And I'm just going to go in and make a little bit of a change here so that I can do the following. Let me go ahead and first comment this now, just so we can keep track of what's been going on this whole time. So dynamically allocate an array of size 3. Assign 3 numbers to that array. Time passes. Allocate new array of size 4. Copy numbers from old array into new array. And add 4th number to new array. Free old array. Remember, if you will, new array using my same list variable. And now print new array, free new array. Hopefully that helps. And we'll post this code online after too, which tells a more explicit story. So it turns out that we can reduce some of the labor involved with this. Not so much with the printing here, but with this copying. Turns out C does have a function called realloc that can actually handle the resizing of an array for you as follows. I'm going to scroll up to where I previously allocated a new array of size 4. And I'm instead going to say this: resize old array to be of size 4. Now, previously, this wasn't necessarily possible, because recall that we had painted ourselves into a corner with the example on the screen where hello world happened to be right after the original array. But let me do this. Let me use realloc for reallocate and pass in not just the size of memory we want this time, but also the address that we want to resize, which again is this array called list. All right, the code thereafter is pretty much the same. But what I don't need to do is this. So realloc is a pretty handy function that will do the following. If at the very beginning of class, when we had 1, 2, 3 on the board, and someone's instinct was to just plop the 4 right at the end of the list, if there's available memory, realloc will just do that. And boom, it will just grow the array for you in the computer's memory. If, though, it realizes, sorry, there's already a string like hello world or something else there, Realloc will handle the trouble of moving that whole array from one chunk of memory originally to a new chunk of memory, and then realloc will return to you the address of that new chunk of memory. And it will handle the process of freeing the old chunk for you, so you do not need to do this yourself. So in fact, let me go ahead and get rid of this as well. So realloc just condenses a lot of what we just did into a single function, whereby realloc handles it for you. All right, so that's the final improvement on this array-based approach. So what now? Knowing what your memory is, what can we now do with it that solves that kind of problem? Because the world is going to get really slow, and our apps and our phones and our computers are going to get really slow if we're just constantly wasting time moving things around in memory. What could we perhaps do instead? Well, just one new piece of syntax today that builds on these 3 pieces of syntax from the past. Recall that we've looked at struct, which is a keyword in C that just lets you invent your own structure, your own variable, if you will, in conjunction with typedef, which lets you say a person has a name and a number, or something like that. Or a candidate has a name and some number of votes. You can encapsulate multiple pieces of data inside of just one using struct. What did we use the dot notation for now a couple times? What does the dot operator do in C? Perfect, to access the field inside of a structure. So if you've got a person with a name and a number, you could say something like person.name or person.number if person is the name of one such variable. Star, of course, we've seen now in a few ways. Like way back in week 1, we saw it as like multiplication. Last week, we began to see it in the context of pointers, whereby you use it to declare a pointer, like int star p or something like that. But we also saw it in one other context, which was like the opposite, which was the dereference operator, which says if this is an address, that is, if this is a variable like a pointer, and you put a star in front of it then with no int or no char, no data type in front of it, that means go to that address. And it dereferences the pointer and goes to that location. So it turns out that using these 3 building blocks, you can actually start to now use your computer's memory almost any way you want. And even next week when we transition to Python and you start to get a lot of features for free, like a single line of code will just do so much more in Python than it does in C. It boils down to those basic primitives. And just so you've seen it already, it turns out that it's so common in C to use this operator to go inside of a structure and this operator to go to an address that there's shorthand notation for it, aka syntactic sugar, that literally looks like an arrow. So recall last week I was in the habit of pointing, even with the big foam finger. This arrow notation, a hyphen and an angled bracket, denotes going to an address and looking at a field inside of it. But we'll see this in practice in just a bit. So what might be the solution now to this problem we saw a moment ago, whereby we had painted ourselves into a corner and our memory a few moments ago looked like this? We could just copy the whole existing array to a new location, add the 4, and go about our business. What would another, perhaps better solution longer term be that doesn't require constantly moving stuff around? Maybe hang in there for your instincts if you know the sort of buzz phrase we're looking for from past experience. Hang in there. But if we want to avoid moving the 1, 2, and the 3, but we still want to be able to add endless amounts of data, what could we do? Yeah, so maybe create some kind of list using pointers that just kind of point at a new location, right? In an ideal world, even though this piece of memory is being used by this h in the string hello world, maybe we could somehow use a pointer from last week, like an arrow, that says after the 3, oh, I don't know, go down over here to this location in memory. And you just kind of stitch together these integers in memory so that each one leads to the next. It's not necessarily the case that it's literally back to back. That would have the downside, it would seem, of costing us a little bit of space. Like a pointer, which recall takes up some amount of space, typically 8 bytes or 64 bits. But I don't have to copy potentially a huge amount of data just to add one more number. And so these things do have a name.